Okay, so I'm going to remind you all first off that it is very, very, very important for you to keep on top of the homework because that is your practice. We do not have time in a college class to do an infinite and endless, a huge number of examples. So I'm doing one or two and then we got to move on to a new concept. Okay, so the number E is a non-terminating, non-repeating decimal. It's like pi, right? If I said, hey, what's pi? Most of y'all would say, hey, that's 3.14, or maybe you'd say 3.14159, or you might even know a few more decimal places, but it's an irrational number, right? And E is also an irrational number. And so you should know it's like 2.71 something, 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 right? But we can approximate it. Your calculator will have an E button on it. GeoGebra, now, if you just say E, it'll know that you're talking about E, the irrational number. See here, I just did E, and it said, oh, you don't want a new slider. You want 2.718, blah, blah, blah. All right, so you can use your calculator, hopefully, to go find, hey, what's E to the 10th? Well, it's going to be about 2.7 to the 10th, right? So if I go E on my calculator here, E to the 10th is going to say, hey, that's 22,026.46579, blah, blah, blah. All right, 22.026. Point, I don't remember, right? Let me get back my calculator here. 4658. 4658. So just know that's an approximation, right? And if I say, okay, hey, what is 1 over E cubed squared? You're going to be like, ah. So first off, you could recognize that that's 1 over E to the 6th, because when you raise a power to a power, you multiply the powers, right? Or you could go ahead and say 1 over E squared to the, sorry, I did the exponents backwards. 1 over E cubed to the squared, all squared. So we've got 0.00247, blah, blah, which would be same as 1 over E to the 6th. Same number, right? 0.0024787. Okay, so you don't, in web work, don't round these things too much. Try not to round them at all, okay? So exponential function E is really just like any other number. It just doesn't look like a number, and I know that makes some of you uncomfortable, right? But it's the same. It's just like 2 or pi or a fraction, 4/3, whatever. So we can use it. It's positive, right? It's not equal to 1. And so we can use it as the base of an exponential function. And you can see here, it looks pretty close to the same as the graph. It looks exactly the same, except for the scale is a little bit different. As the graph that we had of 2 to the x and 3 to the x, it looks the same. Right, except it has the same y-intercept. When we plug in 1, we get 2.71, blah, blah. And when we plug in 2, we get somewhere in there, I don't know. So it's not anything different. It's not anything to be worried about or anything. So what happens is we change the base of an exponential function. So we've got several graphs here, functions to graph rather. We've got 2 to the x, 3 to the x, e to the x, 4 to the x, 10 to the x. And we want to see on GeoGebra, we're going to graph these in GeoGebra and see what happens as we do that. All right, so we're going to have y equals 2 to the x. There we go. I'm going to go ahead and scoot this down a little bit. We've got y equals e to the x. Y equals, we had 3 to the x, is that right? Let's see, 3, 4, and 10. Okay. We had y equals 4 to the x. Let's try that again. And we had y equals 10 to the x. And so as we put these on here, hopefully you recognize or saw or noticed, there we go, that as the base got bigger, my graph got steeper and steeper and steeper over when we were on the positive side of our Cartesian plane. So where x is positive, my graphs from 2 to 10, so here's 2, right? And here's 10. The 10 is growing much faster, it's much steeper than the 2. And we go back and so we have 2 to the x, and e to the x is a little bit steeper. 3 to the x is a little bit steeper than that. 4 to the x is steeper than that. 10 to the x is steeper than that. Right? They're all going through that same 0, 1 y-intercept. And on the other side is kind of the opposite, right? 10 to the x stays really stays small when we're at negative x's for longer than 2 to the x does. All right? So that's kind of our properties there. Sorry, I'm not re-recording, so oh well. All right, so we noticed that as long as our base was bigger than 1, the larger the base, the more quickly the graph increases. It's steeper. All right, so all these graphs were increasing, and the properties were all similar, right? The domain was all real numbers, the range was 0 to infinity, and our asymptote was the x-axis, aka y equals 0. Okay, so for all of those graphs, they were all the same there. Okay, so what about if we have a base between 0 and 1? And of course my A is here. I don't know how I did that. That should be a B. We're going to fix the other one. Okay, hopefully that's the end of the typos, right? So when we're talking about base, we're talking about B. All right, so what if our base is between 0 and 1? All right, so if we look at 3/4 to the x, 2/3 to the x, 1/2 to the x, 1/8 to the x, and we do the same thing here. All right, so I'm going to turn these guys off. We're going to do this, right? Because I don't remember what we had. Y equals 3/4 to the x. I'm just going to put them all in, and then we'll turn them on and off. So 2/3 to the x, y equals 1/2 to the x, y equals 1/8 to the x. Okay. And so you can see here, let's turn these all off, right? So there's 3/4 to the x. Our bases for all 4 of these were between 0 and 1. So 3/4 is, nice decaying or decreasing function. 2/3 x is dropping faster, right? So we are going, from, let's say from 1x over, we're going from about 7.5 to 5. Versus this one, which is a little over 4 to a little over 3, right? So the 2/3 x is dropping faster, is decreasing faster. The 1/2 to the x is dropping even faster until you get into positive x values, and then they kind of slow down a little. Well, no, they're still doing the same thing. And let's see, let's add the 1/8 to the x. So same story there, dropping faster and faster and faster. The smaller the base gets. So that's what we've got here. So for our base being between 0 and 1, that's a decreasing function, and the smaller the base, the more quickly the graph decreases. Okay, so, and again, our properties are all similar. Our domain was all real numbers. Our range was 0 to infinity, and our asymptote was the x-axis, y equals 0. Okay, so we'll do this one, and that'll be the end for this video. So all 4 of the graphs on here are of the form y equals ab to the x. But of course, they have different values of a and different values of b. So I think that the second question is actually the easier one to address first, which has the largest value for a. So we've got a blue, a gray, a red, and a green. And for a, we've just got to look at the y-intercepts, right? So the red is at 3, the black is at 2, the green and the blue are both at 1 for our y-intercepts. And the a value is going to be your y-intercept until you get a vertical translation in there, which we're not doing yet. So which one has the largest value for a? It's going to be the red function. Now, which one has the largest value for b? This is the base. So we can automatically rule out the blue and the black or gray because those have bases that are between 0 and 1. So we've got to look at red and we've got to look at green, and we're going to say, okay, which one is steeper? Which one's growing faster? So if we go from 0 to 1, the green's going from 1 to 4, and the red looks like it's going from 3 to 8. Okay, and this is where you got to remember, we don't want to look at the magnitude, we want to look at the ratio, right? That the green has a ratio of 4 over 1, and the red has a ratio of 8 over 3. So the green one actually wins there. It has the larger ratio. And if I asked the smallest b, we would say, okay, it's either got to be the blue or the black one, right? We would say, okay, which one is dropping faster? And to me, it looks like the blue one, but it's hard to tell because of the different y-intercepts. So we want to pick a couple of points as best we can. So this blue one's going from roughly 7, let's say, you know what, let's say here, that's about 2 2/3 to 1. So the blue, 1 over 2.7, let's call it. And the black is 4 to 2. It's going, and actually I should have done these. I did the blue one correctly, I did the black one incorrectly, so it should be 2 over 4, because it should be the x equals 0 point over the x equals -1 point, right? All right, so these ratios would be your b at x equals 0 over your b at x equals -1. So each one of these ratios is going to be our value for b. So we need to see is, let's see, 1 over 2.7 is about 0.37 versus 2 over 4, which is 0.5. So which one has the smaller b? It was the 1 over 2.7, which is our blue. All right. So next up is everything we learned in chapter 3 about transformations of functions.